Hey guys, this is Sean with Alexander Tutoring. Welcome to Relativity Lecture Day 9. Thanks to all you that have been watching this whole time. It's been a long haul, but it's been worth it. Okay, so last time we came up with this crazy result. We were working with this light clock, right? And the crazy result was that the guy inside the train, he measures the light go straight up and straight down, and of course it moves at the speed of light to him. And so he records a certain time interval between ticks, right? And the whole thing to get is that because he's inside the train, he has no way of knowing that he's moving. He's going at a constant speed, and there's no force of nature that's going to change anything or alert anything to anyone to the fact that he's moving. So the clock should behave just like it would anywhere else, right? Okay, so the light goes straight up, straight down, and he measures a time interval. Now the guy watching from the embankment, well, he sees the light travel a different path. He sees it travel over the click. The light has to travel all the way up to the top and back down as the train moves to the right at speed v, right? So he actually sees the light travel a longer distance. Now, because of postulate number one, everyone agrees on the speed of light. That means that the light beam has longer to go. So there's going to be more. The time interval is going to be longer than compared to the guy in the train's time interval. That's a crazy result. And in fact, we even calculated exactly how much those time intervals would be different. And we came up with Einstein's time dilation formula. Okay, so the clock in the train does not agree with clock outside the train. Now this result is true for all intervals, meaning not just a light clock. When you compared the beat of the heart between the two guys, one would beat slower than the other. The electrons going around the atoms would go slower. So all motions in the train are going to appear to move slower to the guy watching from outside. Okay, so this is a crazy result. Different observers do not agree on time intervals. This is different than what Isaac Newton thought, that everyone in the universe agreed on time no matter what. Okay, so we've kind of built this up. Remember, I asked you what is a second or what is a time interval, right? And then I said, how do you measure it? Well, we need a motion to measure time, right? We need a rotating thing on the wall, or we need something moving to measure off a time interval. Okay, and then how do we all show up to class on time? We talked about simultaneous events. You need to be, your butt needs to be in your chair simultaneous with the clock on the wall's hands, which are considering another motion, lining up at 8 o'clock. Okay, so that's how we're measuring time was with simultaneous events. Now we got to look at simultaneity in the same kind of example here. So check this out. Let's start with the guy inside the train, and always and forever, he doesn't know he's moving, so everything should go down like it would anywhere else. Okay, and what this is in the middle is we have basically like a little laser beam that can shoot light in both directions, and basically it's going to shoot light at the same time in both directions, and the light's going to come this way, hit the front door, come this way, hit the back door. So for the guy in the train, of course, he would see the light hit the front and the back at the exact same time, simultaneously, right? There would be simultaneous events of the light hitting here and here. However, what does the guy on the embankment see? Well, remember the train's moving with speed v this way. And well, what does he say? Okay, so the little laser, the two-way laser fires, right? But as it fires, the train moves forward a little bit, right? While the light's making its way to the front and the back. Now it's the speed of light, so you can see this effect is really hard to see unless you're moving really fast. But what you can see here is that this light beam, because of the train's motion, has farther to go to catch up with the front wall. And then, maybe the back of the train's like right here now. And then the laser beam in the back has less distance to go. So which door, the front or the back, is going to get hit by the light first? Well, you can see that the door at the back is going to get hit first because the light has less distance to go. So we're going to get a light contact with the back door first, followed by a light contact at a later time at the front door. But remember, for the guy inside the train, it happened at the same time. So the simultaneous events of the light hitting the front and back wall for the guy inside the train is no longer simultaneous for the guy outside the train. So what's simultaneous in one frame of reference is not necessarily simultaneous in another frame of reference. So now they don't agree on that either. Okay, so these now we're getting to the real nitty gritty of special relativity. Okay, that's it for today, guys. Thanks for listening. We'll see you next time. Take care.